Okay, thank you.
Okay, the final talk of today is by Professor Michel Waldschmidt, and he'll be talking about on binomial binary forms.
Thank you very much. So I wish first to thank the three organizers of this beautiful conference, and I am especially happy to be here because I was not sure that I would come since I had a very busy schedule, but Amir wrote to me such a kind message that I could not resist, and finally I am here, and I am very glad of that, to see so many friends. And of course I start by wishing a happy birthday to Ram. We know for a very long time. I will not claim that in the audience I am the one who knows you for the longest time, because Kumar is here. But we met in many places, in Canada, of course, in France, and yeah, I think this is the place where we met the most often. And my favorite topic is transcendental number theory, and you are really a specialist of transcendental number theory, and it is thanks to you that so many people in India now are aware of the theory and are working in this theory, and especially in the consequences of the results which are known. Your book is very influential, and you developed a part of the theory which is new, which is application of the results like Baker's result on the linear forms in logarithm, Nesterienko result on the algebraic independence of pi to the pi and gamma, well, pi, well, okay, anyway, this result of Nesterienko, and then also Chanuel's conjecture. And you found some beautiful and unexpected consequences of this result, and it's clear that it's not finished. There are a lot of open problems, and in fact there are many young people who are working in this direction, which I think is very promising. So I am very happy that you had such an influence. My talk today has some connection with transcendental number theory. When I started this sequence of papers, it was with Claude Levesque, who told me, and he told you, that he is very sorry not to be able to come. And we were using Baker's theory, say. After that, we continued with Etienne Fouvry, and after that, I continued only with Etienne Fouvry. And what I will explain is this subject with Etienne Fouvry. And at the beginning, we were not using transcendental number theory, but what is new in my talk today compared to talks which I gave on the similar problems before is that now we are able to use Baker theory to go a little bit further. So the topic is the study of binary binomial forms. So these binary binomial forms are just forms in two variables x, y. So the fact that there are two variables means that they are binary forms, and binomial because there are only two monomials, axd and byd. In the special case d equal to, the quadratic binary forms, this is a very classical subject which goes back to Brahmagupta, Fermat, and others. And an example is the study of sum of squares, which were studies by Ramanujan and Landau. And I will say a few words on the quadratic case, but this is not the main part of my topic. I will say something about the work of Bernet, which is not so well known. I will essentially speak on a binary form of higher degree. And the main result is a result which belongs to Diophantine approximation, and it's close to transcendental number theory, which is a result of 2A, which gives the finiteness of the number of solutions of an equation like axd plus byd equal m. Of course, 2A's result is more general than these forms, but I essentially speak on these forms which are binomial forms. And I give here a list of names of mathematicians who contributed to the theory. The most recent result and the very impressive one is a result of Stewart and Yao Xiao, who gave a generalization to forms of higher degree of the results which were known for definite quadratic forms. I will say a little bit more on this subject after. And now the new part of my talk, which will be the work with Etienne Fouvry, where we investigate the number of integers which are represented by one form in a family of binary forms. The work of Stuart and Yao Xiao is about you fix one binary form and you study how many numbers m are of the form f of xy. But what we do with Etienne Fouvry is to take a family of forms and we ask the same question, how many m can be written as f of xy for some f in the family. So my talk is essentially an abstract of the paper which is to appear in Acta Arithmetica with a reference which is here. By the way, these slides are on my website, so there is no need for you to take some notes. Okay, I start just for the history about binary quadratic forms. I mentioned already the work of Fermat and Brahmagupta. There are essentially two cases, the case of indefinite forms, where there may be, and most often there are, infinitely many solutions. The Brahmagupta-Pell-Fermat equation, x squared minus dy squared equal plus or minus 1. And the case of positive definite forms, where there are only finitely many solutions, and the fact that there are finitely many solutions is obvious. If you fix m, you have a positive definite form. And an example is the sum of two squares. But in spite of the fact that there are only finitely many solutions, there are some problems which are not obvious. For example, to investigate the number of integers less than some bound, capital N, which are sums of two squares. And this was studied by Landau and Ramanujan, and they proved an asymptotic formula, which is that the number of such integers, sum of two squares, is asymptotically a constant times n divided by the square root of log n. And the constant is the so-called Landau-Ramanujan constant, which is given here as Euler product. The study of representation of integers by binary forms is classical. It was done first by Fermat, and then essentially it was completed by Lagrange, but there are also some work of Legendre and Gauss. The case of, well, the analog of the constant of Landau and Ramanujan for positive definite quadratic forms, this has been completely solved by Bernays in his thesis, which was under the direction of Landau. And this thesis exists only in German, and I think it would be interesting to translate it from German, but also translate it in modern language. And the result is that given a positive definite quadratic form, there exists a constant, which is the analog of the Landau-Ramanujan constant, such that the number of integers bounded by n, which are represented by this form, is a constant times n divided by the square root of log n. So this is the situation for quadratic forms. And now we come to forms of a higher degree. The main first result is the result of 2a, which is that if you have such a binary form with non-zero discriminant, the set of integers xy, the solutions of the equation fxy equal m, where m is a non-zero fixed integer, this set is a finite set. This is a fundamental result. It came from Diophantine approximation and from the first improvement of Liouville inequality. In fact, the improvement of Liouville inequality is a consequence of the result on forms. Now that we know that when we fix m, we have only finitely many solutions, thanks to 2a theorem, we can ask how many solutions do we have? And the result of Mahler is about the number of xy such that f of xy is bounded by capital N and positive. F is a binary form of degree at least 3 with non-zero discriminant. And Mahler proved that the number of xy is asymptotically the area of the domain which is defined by f of xy less than or equal to 1. It's not very surprising, but it means that the points which come out of the domain with xy bounded by n contribute for small o of n to the 2 over d. So the asymptotic is a constant times n 2 over d. You can compare the n with the exponent 2 over d with the case d equal to, which would give n. And it was not n for the sum of two squares, it was n divided by square root of log n. So I will come to that just after. The results which I mentioned of two-way and Mahler were for forms of degree d with non-zero discriminant. But in my talk today, I wish to restrict to binary forms of degree at least 3. So for this special case, what we consider is we fix A, B, and D, which are, excuse me, I made the mistake. Okay, so it's good, it's this one, yeah. Okay, we fix A, B, D with A and B, which are different from 0, otherwise it's not binary, and D is at least 3. And a corollary of the result which I mentioned for two-way is that for each m, this equation has only finitely many solutions. And for Mahler is that the number of integers such that axd minus byd less than n is asymptotically n to the power 2 over d, where af is the area of this domain. We have to compute the area of this domain. It is an integral with the binary form, so it's an easy integral, and we can compute it explicitly, and the explicit values depend on the A, B, D, and they involve the gamma function, Euler gamma function. And Stewart and Yao Xiao gave the explicit formulae which are here. So the result of Mahler deals with the number of x, y, but we are interested in the number of m, with m equal f of xy. So we do not want to count twice the xy, we count the m. And the heuristic is the following. There are some numbers which are represented by f and some numbers which are not represented by f. You consider the numbers which are represented by f, and you expect that all the xy which will give this value of m will occur for the automorphism of f. In this case, the number of solutions, m being given, will be wf, something which depends on the automorphism, but does not depend on f, on m. And therefore, in this case, we will see that the number of m is af times n to the power 2 over d, which is the value of which is given by Mahler, but it's less than that. We have a coefficient 1 over wf. And this is a heuristic. It's not true like this, but the conclusion is almost true. Instead of 1 over wf with some integer here, we have some number which depends on the automorphism of the form. And this is the result of Stewart and Yao Xiao, which was published in 2019. You fix a binary form of degree at least 3 with non-zero discriminant. You look at the number of integers bounded by n, which are of the form m equal f of xy, with xy in z square. And this number is asymptotically afwf n power 2 over d plus a big O or something which is smaller. The exponent is less than 2 over d. So you find again the wf n 2 over d, but you have the af n over 2 over d, but you have a coefficient wf, which is at most 1, and which depends on the automorphism of f. What is the value of wf for these binary forms? It's completely explicit. It will be 1 if a over b is not the dth power of rational integers and d is odd. It will be 1 over 4 if a over b is not the dth power, but d is even. And otherwise, we have some values. If a over b is the power of a rational number, then wfabd is less than 1, and it depends whether d is even or not. So it's completely explicit. which is not the case in the more general situation. This result of Stewart and Yao come after a long list of papers which were studying exactly the same problem, but in very special cases. For example, the case d equals 3, d equals 4, for some specific value of a and b. And it's really amazing to see that they succeeded to get a complete result which is uniform and which contains essentially all the results which were obtained by the people who work on that before. And there is here a list of some of the papers. You see there are some papers on binary cubic forms, binary quartic forms, and so some very special cases. But now all this is contained in the work of Stewart and Yao Xiao. Okay, now I come to the new results which I want to discuss. And this is a joint work with Etienne Fouvry. We started with cyclotomic forms, but I will not mention these cyclotomic forms. This was a joint work with Claude Levesque. After that, we studied with Etienne Fouvry families of binary forms to see which kind of result which we could obtain. So the idea is the following. We take a family of binary forms, F. Each binary form has a non-zero discriminant, and if we fix a given degree, there are only finitely many forms of this degree. And we want to find some assumption for which the conclusion will be that the number of integers which are represented by elements of degree at least d in F is asymptotically the number of integers which are represented by elements of degree exactly d. So we have to prove that the forms of higher degree do not contribute to the main term. And so this is the goal that we have. And we have many examples where the conclusion is true and many examples where the conclusion is not true. So I will explain a little bit. The first thing that we need to discuss is if we have two forms which are not isomorphic, we want to know whether there are many integers which are represented by the two forms. And the conclusion is no, we do not have many integers represented by two forms. The number of such integers will be a small o. Okay, so I made a mistake. Okay, it is a small o of n to the 2 over d. So two forms are said to be isomorphic if there is a matrix in GL2 of Q such that F1 of AX plus BY, CX plus DY equal F2 of XY. It's not quite obvious, since we are interested with the integer points, that we should take a GL2 of Q or GL2 of Z. And it turns out that we need to work with GL2 of Q. So A, B, C, D are rational numbers. It's easy to see that two binary forms which are isomorphic have the same degree. And the preliminary result which we proved is that if we have two binary forms of degree at least 3 with non-zero discriminant and which are not isomorphic, then the number of integers which are represented by both forms is big O of n to the power 2 over d. So represented by two forms means that we have... Excuse me? Little o, yes. Yes, or little o is because, well, otherwise it would be trivial. Okay, so... yes, I always confuse the two buttons. In the work of Stewart and Yao Xiao, what they discuss is they take one form and they study how many integers are represented by this form, but in two ways, x1, y1. So they take f1, f1 equal f2. But in our work, we take f1 different from f2. And so this is a generalization of the work of Stewart already at this point. Well, it's a variant, not exactly a generalization. So now what I want to discuss is the special case of binary forms. So this is a recent paper with Etienne Fouvry. So we will take a set of forms which are binomial binary forms, AXD plus BYD. And for each form, AB is different from 0. So F will be the union of FD for d greater than or equal to 3, fd is a finite set of binomial forms. So we want to give an asymptotic formula as n tends to infinity for the number of m for which there exists a d prime greater than d and f in fd prime, xy in z square, such that fxy is equal to m. So we take all the form of the family of degree at least d. I first give some trivial example, which is that if you take the variables xy, which are 0, 1, or -1, then you have something which is essentially trivial. The value of this form at 1, 0, 0, 1, 1, 1, and 1, -1, and so on, are just given trivially. And because of that, it's natural to assume that the maximum of xy is at least 2. I will come back later to give a precise example for that, but I want to explain why we assume this assumption. Otherwise, it's trivial. So the expected result is the following, and I will give some sufficient conditions for which the expected result is a theorem. We consider the number of m bounded by n for which there exists d prime and some binary binomial form in fd prime, xy is z square, maximum of xy greater than 2, and so that f of a, b, d prime, xy is equal to m. And we want to prove that the number of such m, so asymptotically when capital N tends to infinity, which satisfies this condition, f a, b, d, xy equal m, is asymptotically the sum of af, wf, n to the power 2 over d, and the sum is about the form abd in fd, which means that the forms of higher degree count for a small o of n to the 2 over d, and also if you take two abd and a prime b prime d with the same d, then we do not count twice the same forms. So this is what this is the theorem, but I want to say what are the hypotheses. This is what is missing so far. So to prove such a result, we need two tools, two auxiliary results. The first one is to make sure that we do not count several times the same m, as I just say. And the second thing is that if we take d prime sufficiently large, then the numbers which are represented by a form fd prime contribute only to the error term. D prime sufficiently large is sufficient, because if we prove that for d prime greater than d0, then the forms which have degree d, d plus 1, d plus 2 up to d0, for each of them, we can use the result of Stewart and Liao-Xiao, and we have the expected result. But we have to check that the forms of very high degree will not contribute to the main term. So for the first result, we need to make sure that two forms in our family are not isomorphic, and the result is not too difficult. It is the following lemma. We take two forms, axd plus byd and a prime xd plus b prime yd, with the same degree, because we are interested with isomorphic forms. These two forms are isomorphic if and only if either a over a prime and b over b prime are this power, or a over b prime and b over a prime are both this power. So this is a lemma which is an exercise for the proof. And so this will be our assumption that 1 and 2 are satisfied for the forms in our family. Now, the second tool that we need is an asymptotic result. And for that, we do not have the full statement in generality, but we have at least some good examples. And there are two ways of getting the desired result. The first way is rather elementary. We assume that all the forms in our family are definite positive. And in this case, the only assumption that we need to add is on the number of forms in each FD. So this is one way that is elementary. But the main new fact is that we can use low bounds for linear forms in logarithm, and using this kind of tool, which is very powerful, we can get some more general families of binary forms. We only need to have an upper bound for the coefficients A and B of the forms. We do not need it in the first case, because if the coefficients are large, then the values of the forms are larger. So, but in the case where the forms may have some real zeros, then we need an assumption on the coefficient AB, and we know that this is necessary. So the result will be the following. We have, for each integer d greater than 3, a subset of AB, of A and B are strictly positive. This is ED. Now we denote by FD the family of binary forms AXD plus BYD, where the AB are in ED, and F is the union of this set of forms. And we count the number of M which are represented by one of the form of degree at least D in the family. We denote it by R sub greater than or equal to D of N, the number of M, so that there is a F of degree at least D with Fxy equal M, and we add the maximum of xy greater than 2. And we have the assumption that two forms in the family are isomorphic if and only if they are equal. So we have two results, and the first one is for the family of positive definite binary form, binomial binary form. So the only assumption that we have is that the number of elements in ED does not grow more than an exponential of D. And the second theorem, which do not assume that the forms are definite positive, we have an assumption on the maximum of A and B that it is bounded by exponential epsilon D over log D. And in this case, we have the conclusion that we expect, which is that the forms which count are only those which have degree exactly D. The one of higher degree do not come into the picture. Which one? Oh, ED. It was just okay. ED is a finite subset. Oh, yeah. ED is a finite subset of Z, and the form FD are the forms AXD plus BYD. So ED is a set of AB. The assumption which we have on the size of the AB, which is exponential epsilon D over log D, is probably not the right one, and the right one should be exponential epsilon D, or maybe a constant time D, but the log D which is here should not be there conjecturally. And why do we are confident that it is so? It's because, maybe I go directly to the conjectures. If we use either the ABC conjecture or conjectures on lower bound for linear forms in logarithm, which are conjectures in the book of Serge Lang on the elliptic curve Diophantine analysis, then this conclusion here can be replaced by exponential epsilon D. It's quite interesting that the two conjectures give exactly the same result. ABC conjecture or conjectures on lower bounds for linear forms in logarithm, they come from different sources, but they give the same result, which I did not expect. Let me give some examples. The fact that the assumption maximum of xy greater than 2 cannot be omitted can be obtained by taking the sequence AD xd plus yd. You take the sequence AD, which is 1, 2, 1, 2, 3, 1, 2, 3, 4, and so on. And in this case, you see that FD of 1, 0 is AD, FD of 1, 1 is AD, and for each M, you have infinitely xy, so for which fxy equal M. So this is not compatible with our result. So we have to assume that the maximum of xy is at least 2. And also the assumption on the number of elements in ED, in the case of positive definite quadratic forms, cannot be omitted. And for that, we take the forms AXD plus B plus YD. So we will take, we take x equal 2 and y equal 1. So we look at the numbers f of 2, 1, which are a 2 to the d plus 1. And there are 2 to the d positive integers of this form. and this is more than the result that we have. So this assumption cannot be omitted. We are just at the limit. So we are not so far from the best possible result, apart from the fact that some conjectures suggest that we can have a small improvement, which we do not know how to do without any further assumption. So thank you very much.
Any questions?
Binary forms, or because we consider binomial forms rather than make a transformation and make it a non-binomial form, right?
Okay, in the work of Stuart and Yao Xiao, they consider binary form, but not only. They consider general forms, and it's also GL2 of Q which comes into the picture. So GL2 of Q is really attached to this number WF, which is defined for any form, binomial or not binomial.
Any questions from the Zoom?
There is a question. Yes, Cam Stuart. Oh, I am glad to hear you, Cam, because I wanted to tell you that, do you hear me? Do you hear me, Cam? Yes?
Yes, I hear you, Michel. Lovely
good.
talk. Really enjoyed it.
You know that Etienne
The
and
check will
myself,
be in the mail.
Yes. Etienne Fouvry and myself are expecting an answer from you. Do you know that? Okay, I will send you again. I will send you again the result, but the message of Etienne. But congratulations for your result, which is extremely useful for us. I remember that you mentioned it for the first time in Lecce. It was, in 2016, and it was a conference for me, and this is where you announced this result. And I did not expect at that time that I would work so hard on your paper.
Well, I'm delighted that you have. You've got really lovely results there, Michel.
Thank you.
Now, is there any chance? Now you focused on binomial forms. I guess there would be some possibility of extending that more generally.
Okay, I have a paper which is not complete, but with Etienne. If I tell you that it will on trinomial forms, you may expect that the next one will be on quartic forms. It's not exactly on that. It is on lacunary forms. And lacunary forms will include trinomial forms. So we have some results on trinomial forms, not as general as for binomial forms.
Oh, very nice, very nice. I look forward to seeing it, Michel.
Okay. Thank you.
So any more questions, comments? If there are no more questions, comments, let us thank Professor Waldschmidt as well as all the speakers of today.
Thank you.
We meet tomorrow at 9.